I'm now recording. So are there any questions before I get going?
I don't think I have any right now.
Okay. Yeah, just chime in at any point if I say something that isn't clear or some thought pops into your head. Let's see, Jason looks like Jason just joined us too. I'm going to write down. Hey, Jason.
Sorry I'm late. I just came from my other class.
That's okay. So your other class is another University of Phoenix class?
No, it's a community college class in person
Okay.
in anatomy.
So you deal with live human beings there, face to face.
Something like that.
That's
Yep.
good. All right.
Yeah, it's fun.
Okay, so I've got it going here. I have a presentation that I threw together a while back that's more or less related to the material of this week. So let me get that going here. So basically I'm asking, well, you see what the question is, how far have we come since 6 Easy Pieces? I think I mentioned it in the announcement for the meeting, but I don't know how many of you are aware of this, but the content of 6 Easy Pieces, our textbook, which all of you, I encourage you to be reading it. I sometimes think some students don't even know it exists based on some of the essays sometimes, though most of them are fine. But that book was based on lectures delivered by Richard Feynman between now I'm trying to remember, I think 1962 and 1963. In many ways, it's just as relevant today as it was then. Physics is a pretty mature science. There's some things that he talks about that are open questions in 1963 that have been pretty much resolved by now. But really the picture of nature that Feynman had 60 years ago is very similar, pretty accurate. In fact, Feynman is one of the main architects of modern physics. So, and I think I may have said this last time, but Oppenheimer, the movie, was a big deal recently, and one of the characters, not really named in the movie, but he was in the background, was Richard Feynman. Not the real Richard Feynman, obviously, an actor portraying Richard Feynman back in those days. He was the guy playing bongo drums at the parties, and I think even out on the desert when they were getting ready to test the bomb. But he did more than just play bongo drums. All right, so the question is, where were we in 1963? This was something that was really irritating people like Feynman and Enrico Fermi. Enrico Fermi is up here. I got a quote from him that really summarizes the attitude back in those days. It said, if I could remember the names of these particles, because they were doing experiments to study how, a very crude way, if you had a watch, a mechanical watch, and you wanted to know how it worked, how it was made up inside. Well, of course, you could be very delicate and maybe get tiny little jeweler's screwdrivers and delicately take it apart and see all the little gears in there. But if you didn't have those tools, you might just hit it with a hammer and smash it open and see what's in there, and hopefully you didn't damage it too much. Well, that's really the only tool we have to study matter at the most basic level. That's what these so-called atom smashers do. They collide elementary particles together and see what happens. Well, when they were starting out, I can't really put myself in their heads at the time, but I think they assumed that if you crash protons together, you'd maybe get more protons or or some particle that proton's made up of, but a fairly simple picture. But they started finding that there were all these other particles, prior to the, if you go back 100 years to the time of Niels Bohr, when the model of the atom was first being put together, there were basically 3 particles in the known universe. They were protons, neutrons, and electrons. But after a while, there were not just electrons, but muons, which is similar to an electron, but heavier. And then there were tauons, which were heavier yet. And all these different particles started coming up. And something that, I don't like to overgeneralize, but because they're very related, but chemistry and physics are pretty related, really, and physicists can be arrogant. So if I sound arrogant, just understand that. But really, chemistry, the foundations of chemistry were laid down by people we would call physicists today. But then physicists are always interested in the basic underlying explanation of everything. So once they figure something out, then they leave the details to other people. So the chemists are working with the details that physicists got bored with. Physicists already know that atoms are made up of protons and neutrons and electrons, and the way they interact, they have a basic idea of how they interact, but why worry about all those details? Let the chemists worry about that. And of course, chemists, they're interested in the details of the formation of compounds, the interactions between atoms and molecules, but they're not so interested in how those build up into animal cells. So leave that to the biologists. The biologists are more interested in that. Of course, that's a branch of biology that's like cellular or molecular biology, and there's all different areas of biology. I mean, in a sense, it's all science. Physics is not, we like to compartmentalize everything, but physicists are basically scientists who are most interested in the fundamental explanations of things. And then as things get a little more complicated, chemists deal with that. And then more complicated still, it's biologists deal with those really complicated systems. And, physicists physicists use a lot of math because they're able to use math because the systems are simple enough to analyze mathematically, whereas chemistry, you can't write an equation down usually for some of the reactions that are occurring. You have to model it in a computer with very complicated code and everything, or just experimentally observe it, and write down a bunch of rules. So physicists don't like all these things, all these names of things. They don't want to memorize a lot of things. They want a few simple rules and then understand how it works and, leave the details to other people. So that's what was going on at the time. They were starting to get a little sick of physics because they started finding all these particles, and they didn't know why nature needed so many particles. It didn't make sense that nature needs so many particles to make the known universe. By particles, I mean types of particles. Obviously, lots of particles are needed, but why so many different types of particles? So it suggested there was an underlying, more simple explanation for things. Okay. All right. Boy, that was long-winded, but anyway, that's what I said. Well, a physicist, chemist, Mendeleev, I guess, was a chemist, would have thought of himself more as a chemist, although I'm not really sure. But he laid down the periodic table, and the periodic table was, he just recognized there were patterns in the elements, that certain elements behave the same way. Like in the first column here, you have hydrogen and lithium and sodium, potassium, it's hard to read, rubidium, cesium, and francium, okay? So all these elements actually behave similarly, even though they're much different. 2 hydrogens combine with oxygen to make water. Well, if they're in the same column, I automatically know that 2 lithiums will combine with oxygen to form a compound, and 2 sodiums will combine with oxygen. 2 potassiums will combine with oxygen to form a compound. The reactions are very similar. I mean, the resulting compound might be a lot different, but the chemical formula looks similar. So that meant there was some underlying pattern, and it all made sense when physicists realized that atoms are made up of protons and electrons, and of course neutrons too, but neutrons are neutral in charge and don't really play a big role in chemical reactions. They just affect the mass of the atom. So if you knew how many protons there are in an atom, then you knew which column it would be in. So, you know, you could figure that out by the rules of how many electrons are in the electron shell. So I'm not saying it's real easy, but the fundamental reasoning is fairly simple. You know, it's just based on protons and electrons, and if they look similar on the valence shell of the electrons, then they behave similarly in a chemical way. So the periodic table was the first big clue that atoms are real and that atoms are made up of subatomic particles. Okay. So, you know, a chemist might say, why does nature need so many elements? You know, it's not really necessary. We understand why you need hydrogen and oxygen and carbon and a handful of other elements. I mean, with that, you can phosphorus, and iron. Life is based on those, but why so many other ones? And it's just because they're a consequence of the ways you can combine protons, neutrons, and electrons. You have those basic building blocks and you can put them together, and there's certain rules to follow, but you can put them together in a whole host of complicated ways. Now, that reminds me that I created a link there, and this illustrates what I was talking about. So, these simulations, the simulations you're using for your assessments, your weekly assessments, there's a whole host of them. So I do encourage you to look at some of the other simulations that are available. Here's one that's called Build an Atom, and it shows the relationship between what's in an atom and where it lies on the periodic table. So if I simply put a proton there, well, you see hydrogen shows up. So basically hydrogen is the simplest atom, which has a proton in the nucleus. But you see that a proton by itself is charged. That's why it's called a positive ion. I'm going to also click the stable versus unstable button box. So nature, if you have a positive charge, it's not going to stay positive very long because there are a lot of negative charges floating around. So it's going to grab an electron and become neutral. So to make a neutral atom, we need an electron out here. Now I have your normal run-of-the-mill hydrogen that goes into water, H2O. Now I can change this without changing any of the chemical properties by adding a neutron. So it's still a neutral atom. It's still identified as hydrogen, but obviously there's a neutron there now, and it makes it heavier. So physicists, with all their ingenious naming, their nomenclature, they call this heavy hydrogen because it's hydrogen, but it's heavier. Or you could call it deuterium because there's two nuclear particles in the nucleus. I can add another.
I
Was
just
your
have
comment?
a quick question. Yeah, do you use heavy hydrogen to make heavy water? I've heard of heavy water. I wasn't really sure what it was though when it was explained.
Yes, that's exactly it. You use 2 heavy hydrogens and 1 oxygen to make heavy water. So its properties are the same as water. If you poured it into a glass, you could drink it. It wouldn't hurt you. But if you measured its mass against regular water, it would be a little bit heavier because you have that extra proton or that extra neutron there. And since there's two hydrogens, you'd have two extra neutrons. And a neutron has the same mass as a proton. So, yes. And I can add another neutron. But you see it says it's unstable. This will disintegrate eventually and form an isotope of helium called helium-3. This is called, some people call this super heavy hydrogen or tritium because there's 3 particles there. But it doesn't last forever. This doesn't want to stay like that. That neutron is going to emit, let me remember here. So that neutron will emit a beta particle, which is a negative, an electron, but high energy. And it's going to become a proton. You're going to have 3 protons inside, and that gives you, oh, I'm sorry, wait, let me think a second. You're going to have 2 protons. One of those neutrons is going to emit an electron. It's going to become a proton. You'll have 2 protons and a neutron, and that's helium. Let's do that. Let's take that proton away. Let's just pretend it decayed, had a nuclear reaction, and became a proton. I'll put that in there. See, now it's helium. Now it's charged. It's an ion, so I need to add another electron. So now you see the jump to the other column here for helium. And I mean, I could go on and talking about isotopes and stuff, but I'll just start adding more protons. That's an isotope of lithium that's not stable, so I need to stabilize it. I'll put some more neutrons in there. Okay, so this is a stable isotope of lithium. And now it's neutral. It has 3 electrons, 3 protons, and 3 neutrons. This is lithium-6, okay? This is a familiar isotope of lithium, a common one in nature. And then I can just keep building up the periodic table by adding a proton and electron each time, and possibly a neutron to stabilize it, okay? So there's beryllium, a stable isotope of beryllium. And you see how it's working now. So now I've created boron, add another carbon, I'm going to have, or add another proton, I'll have carbon. But this is carbon, I've lost track of how many, looks like 1, 2, 3, 4, 5 neutrons, and it's 1, 2, 3, whoops, 1, 2, 3, 1, 2, 3, 4, 5, 6 protons, I guess. 1, 2, yeah, 6 protons. That's carbon. Carbon 12 is the most common isotope of carbon, I believe. So I want 12 particles here. 1, 2, 3, 4, 5. So I need 1 more to make a 12 and see it's stable. All right, so you've seen enough of that. There's other things here that are kind of fun if you want to turn it into a game. You know, they have different kinds of games here. So you have to figure out if there's 7 protons, 8 neutrons, and 7 electrons, what would that be? Well, you count the columns here. You go from hydrogen, that's 1, helium is 2, lithium 3, 4 beryllium, 5 boron, 6 carbon, which just had 7 would be nitrogen. And then the question is it neutral? Well, there's 7 protons, which is 7 positive charges, and that's balanced by 7 negative charges. So it is a neutral atom. And I'll check my answer, and I'm right. Okay. This is as simple as you can get. We have a proton and electron. That must be hydrogen. And again, the charges are balanced, so it's neutral. So, okay, let's just do one more and then we'll stop. So let's see, we had 7 was nitrogen, 8 would correspond to oxygen, but we have 10 electrons. that's more electrons than protons, it's going to be negatively charged, so that would be an ion. Okay. All right. So anyway, all this complexity, the basic point is that all this complexity here is due to the combination of three fundamental particles: protons, neutrons, and electrons. And then there's some rules for combining them because, you know, not all of them are stable. But basically, your building blocks, there's just three. So you can explain this whole table, all that complexity, in terms of three basic particles. So that was the thinking behind trying to explain now the proliferation of what were considered to be fundamental particles. There must have been a more fundamental layer to nature than, you know, protons and neutrons, and then pions and kaons and all these crazy particles that were later discovered in the atom smashers and in cosmic rays. So this is what they came up with, and this is still today what's called the Standard Model, and this explains very well everything that we observe in nature. So protons are no longer considered fundamental particles. Protons are made up of what are called quarks, and so are neutrons, and so are these other particles in this table. If I go back to this table here, we have all these. So an electron is considered fundamental. So we don't know of anything that makes up electron. So electron seems to be fundamental. But then you see these other things like pi, these pi symbols. That's a pion. These Ks, so it's a kaon. Of course, the neutron and the proton. And there's these, I think these were delta particles and sigma particles and psi particles, you name it, all kinds of, and the numbers even grew. This was 63. By the time the 1970s came around, there were hundreds of these things. And they were trying to explain why they even exist. Well, they exist because there's an underlying, more simple explanation. And it's done in terms of 6 fundamental quarks. These are shown here, and they have kind of weird names. They call them up, down, charm, strange, top, and bottom. Or some of the physicists more on the California side of the world call these truth and beauty. Okay. And then we have the electron as considered a fundamental particle. These are the leptons. These particles here are called leptons. They, because of their charge and spin, their angular momentum, stuff like that, they have similarities to them. Okay, you have a muon, which is very much like an electron except heavier, and a tauon, which is heavier still, but it has the same properties as an electron. In fact, you can coax a muon to orbit a nucleus and form an atom with a muon instead of an electron. And I suppose you can, I don't know if they've actually done it with a tauon, but I think in principle you could. Okay. And then these are neutrinos. These are other, what are considered elementary particles. Okay. And then the problem is, and this is getting a bit out of my depth, but, you know, physicists want to understand a lot of things. I mean, they want to understand, basically, they would like to have one answer for everything if they could, but, you know, nature doesn't work that way. But there's particles that transfer the forces. They're called vector particles. The electromagnetic field, the force between charged particles, is actually communicated by virtual photons. Photons are jumping. If 2 electrons come together and are pushed apart by their, you know, opposite charges repel, that force is transferred by the exchange of a photon. And to get an idea of what I mean, imagine you and a friend are sitting, you're sitting in a canoe and your friend is sitting in a canoe. And let's say your canoe is full of watermelons. Well, let's say both of them have a bunch of watermelons, and you start tossing those watermelons back and forth to each other. Those watermelons carry momentum. And after a while, your boats are going to be pushed apart. You're going to be too far apart to even toss those watermelons to each other. Those watermelons are exchanging. You can think of I mean, it's a crazy analogy, but you can think of a watermelon field. Instead of an electric field, a watermelon field. The watermelon is conveying the force, it's exchanging, it's allowing you to interact with your friend. And in this case, the way that the interaction works, it's a repulsive interaction. You guys are pushing each other apart by throwing watermelons back and forth. Well, instead of watermelons, you can exchange photons. You can exchange particles called W particles. That's for what's called the weak force. You can exchange pions. That's the strong force. And then you can exchange force between quarks within a proton or within a neutron or within a pion even. You can exchange the force. It's called the color force. They use it just because there seems to come in three varieties. It's exchanged by a fundamental particle called a gluon. Instead of a photon, it's called a gluon. Okay, so it gets a little bit crazy, but the point is it works. But to make it all work and to make the masses of these particles come out right, they had to suggest, and this was done back in like 1965, a physicist by the name of Peter Higgs said, for all this stuff to work out, there must be one more particle, fundamental particle called a Higgs boson, and it's what gives things mass. It creates a Higgs field, and that was discovered. It was discovered at CERN several years ago, and people got a Nobel Prize. But Higgs predicted it, like at least 50 years before it was discovered. Pretty amazing, really, that some guy wants consistency between particles in a model and proposes a solution to that, and then people searched for it for a long time and finally found it. That's something to be pretty proud of. But this is a fairly simple picture. You have 6 types of one particle, 6 types of another particle, then you have this Higgs particle, and then the particles that exchange the forces. So you have the photons, the gluons, and then these W and Z particles that exchange the weak force. But there's one thing missing from this picture. This explains the nuclear force that holds protons and neutrons together. It explains the electromagnetic force, the force between charged particles. It explains the weak force that's behind the nuclear decay. That's 3 forces that are accounted for here. But we know there's a 4th force, and that's called gravity. And gravity has not been able to be incorporated into this picture. That's still the missing piece in physics. Physics has not figured out how to fit gravity in with this picture. And that's where we are now. So the picture as it goes works very well. Some people say, what's the problem? So what? Gravity is something completely unrelated, some fundamentally different thing than these other forces. So we don't need to come up with, some all-encompassing explanation. But some physicists are stuck on the idea that everything has to be unified with a, one or just a few simple, quote unquote, simple explanations. It's simple in a way. Of course, making it all work out can be very complicated. But that's where we are today, and that's where we've been actually for the last probably 40 years. Physics has culminated in what's called the Standard Model, and it's become so successful that a lot of physicists are unhappy because it's worked so well, because it predicts everything they see, and they can't find anything that hasn't been predicted. by the model. Now there are, if you follow, go on YouTube and look at all the speculative things in physics you read about or see things about dark matter, dark energy. These are hints that there's something out there that we don't understand at all, which may be real. There might be something out there called dark matter that we can't detect on Earth for some reason, but has effects by gravity. Or it could mean that something's wrong with our understanding of gravity, and we interpret that as being due to some kind of mysterious matter out there. So we really don't know yet. Okay, so I hope I said enough to, well, I don't know. I hope I didn't thoroughly confuse you, but I just want to give a little story there about modern physics, how we got to where we are. And now you can interrupt me at any time if you want. But what I plan to do is to just kind of step through this week's our assessment simulation. Okay. So I'm going to look at this as a student. And by the way, I encourage you, I mean, if you're kind of interested in this stuff, and since he's the author of the book we're using, to look up Richard Feynman on YouTube. There's a lot of interesting interviews with him. He's a very, some people can be annoyed by him, but he's a colorful character and has a very, at least for some people, a very engaging personality, and he's good at explaining things. So you might look up some of his videos. He's more colorful than your average physicist, let's say that. I mean, he passed away, but also he became very well known outside of physics by being on the commission investigating the Challenger accident back in the 1980s. And he's the one who dramatically showed why the space shuttle blew up shortly after launch. So that got him a lot of press. All right, so this week's simulation. Go here. Start the attempt. So I always, right here are basically, I've described this for the previous simulation. These are prompts that you should take seriously when writing your essay. And, I kind of encourage you to make it easier for me to grade, to maybe break it down into sections. So, first describe what you did in the simulation in your own words. It might just be a couple sentences, but just say what you did. I pressed this button. I put the simulation in slow motion, or whatever it was for that simulation. Then describe in another paragraph. You'd say, while performing simulation, I raised the temperature and I saw the atoms doing whatever, and and maybe say what the temperature was or give some examples of temperatures. I mean, I don't want it to be super long, but I'd like to see a few numbers in there. Come up with a question, at least one question. You might know the answer, and you can answer it in your essay if you want, or you can just leave it open. And if I can quickly come up with something to say in response to your question, I might do that in the rubric responses. Discuss 2 specific ideas from the reading. By reading, I'm referring to chapter 2 of 6 Easy Pieces. So your textbook. Some students go out and use Wikipedia and they say something, and it might be perfectly right what they're saying, but they're not taking it from the textbook. I want the textbook to be your primary reference. Okay. Discuss how the observations relate to developments in the understanding of atomic motion, classical physics. So, say something like, start your discussion out by saying some of the my observations relate to developments in the understanding of atomic motion by showing me blah, 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 So it's clear to me you're responding to that prompt. I want to know that you're responding to it, and then I'll look at how you responded to it, because it's hard for me to search through things and try to figure out, are you actually responding to everything you should respond to? It becomes hard after reading, I have like 30 of these essays I have to read. Believe me, it's not easy going, because I do read them. Use of references. So list your references at the bottom, and I expect one of your references to be 6 Easy Pieces by Feynman, okay? Check your spelling, write like an adult, and you'll be fine. All right, so I got that out of the way. Now we download the assessment guide. Okay, so it's a Word document. Open it up. I like to slide it off to the side here. Makes it easy to refer to. And now I have everything in the world opened up. Now I have to find I guess that's it. Okay. There we go. All right. And then open the simulation. Okay, what does it say here? Click phase changes from the home screen. There's phase changes, so click on that. From the atoms and molecules menu on the top right, select neon. Okay, well, by default, it selects neon. Good. Note the reading on the thermometer and pressure sensor near the top of the container. Okay, well, I'll leave it to you. I won't say the numbers, but you see these numbers. Write those down. Say something like, when I started the simulation, the temperature was whatever it is, and the pressure was whatever it is. Okay, and then it says push the lid of the container down so there's less space in the container. Observe and note what happens to the temperature and pressure. So I'm going to start pushing down slowly and notice what is or is not happening as I lower the lid. But just lower it slowly and note when something does happen. Okay, well, it looks like something's happening now. So, and describe qualitatively, in words, what you see happening, and maybe give me a pressure and a temperature at a couple different places. Okay, you see that as I push down, things are changing. If I push down too much, you'll see they change a lot. Okay. So there, describe what you observed when you did that. And that's the first, that's that part of the simulation. Reset it. Okay, there's the reset button. Note the reading of the temperature. Okay, this gets boring, but write down what you see again. Now we can add more particles by pumping the pump. So I'm going to do that. I'm going to start adding more particles. And just pay attention to temperature and pressure and see what's happening. Describe it as you pump particles in. Some people even estimate how many particles they pump in. I leave that up to you if you want to go to that extreme. But you see it's changing as I run the pump here, up and down. So do that for a while and report what you see. Okay. All right, reset it again. And then it says cool the container by clicking and holding the slider to cool. So I'm going to remove heat from, I'm not adding cold, by the way, I'm removing heat from this. Heat is a thing, cold is not a thing. Let me move the, okay. So, you know, do that, see how low the temperature can go, write it down, write what you see. Then heat the container by clicking and holding a slider to heat. So this is very much like the first simulation, this part. Okay, report what you see. Continue to heat the sample until the thermometer reaches the highest possible reading, whatever that is, okay? So try to see if there is a highest possible reading and what it is and why you say it's the highest possible reading. Okay, that's it. I've done everything you need to do in the simulation. Now you have to maybe come up with a question, relate what you see to what you read in chapter 2, or in addition, chapter 1. If there's something in chapter 1 that relates to this that you want to talk about, go ahead. You know, make sure you give references, ask a question, check your spelling, punctuation, and then that's it. That's what I'm expecting of you for this simulation. All right. Any questions about anything? Let's see who all is here. So I have Brianna, I have Melinda, yes, Marissa has joined us, and Jason. So Marissa, I'm not sure when you joined us, but I've made a note that you're here. So any questions about anything? If not, I've said all I have to say, and I'm ready to say goodbye.
I have a good question.
Okay, go ahead.
I know you already wrote it, but I'll just ask again. You probably won't post the grades for the first report till like the weekend. Is that right?
That's right. Yeah. I've just started grading those essays.
Yeah, I think
I usually find that I can't sleep at 3 a.m. and then I'll work for a couple hours, and it takes a while. But yeah, I've started, and I should get it. I always shoot for Saturday. I'll try to get it all in by no later than Saturday.
Yeah, I guess at least for me, when I write things, that first like set of feedback is really helpful to understand.
Yeah, I know.
If you're understanding the assignment, so that's all.
Yeah, I sympathize with you. I understand. But you know, I'll get in by Saturday. You can submit your essay earlier for this week, and always, if there's something in my comments, you can modify it, right? You can upload another version. I'll always grade, unless you ask me otherwise, I'll grade the most recent version, the most recent submission. Okay.
Okay, thank you.
Yep. Any other questions?
Yeah, the Higgs particle you were talking about, was that the same particle that CERN was trying to call the God particle?
Yeah, it is. Yeah.
Okay.
I'm not really fond of that name. I mean, why would you call a particle a God particle? It didn't create the universe, but it plays a very important role because somehow it couples to matter. You know, it's almost a philosophical question. What is mass? Where does mass come from? What's inertia? Why does mass resist being accelerated? If you push on something, why do you have to push harder to make it go faster? You know, I mean, that's what gives stuff mass. Where does it come from? Well, the Higgs particle somehow it almost acts like a drag on things. So more massive things have more interactions with the Higgs field than less massive things. So somehow it explains the existence of mass, which to me is mind-boggling. So I guess, you know, it's a very fundamental particle for everything. And of course, people want to sell books, so they use catchy names like the God particle. People see that on the cover of a book and they want to know what that's all about. If you said the Higgs field, discover the Higgs field, oh, Higgs is a boring name, you know, but the God particle, that sounds cool. So I think it's more about selling books than anything else.
Yeah, I just think it's I guess it's interesting, but it is hard for me to wrap my head around because it's hard to explain why, even if you have a lot of facts, I think.
Yeah, but you know, like I like to say, um, you know, like relativity, Einstein's relativity is a very non-intuitive thing. And and general relativity is even less intuitive. When you think about what is gravity, he describes gravity as the geometry of space-time that, you know, we normally move around in three-dimensional space. That's what we think of, right? Up, down, left, and right. And in and out, back and forth. Up, down is one dimension, left, right is another dimension, and in and out is another dimension, three dimensions of space, X, Y, and Z. But it turns out time can be treated as like a fourth dimension. And if you treat it that space-time is not linear, somehow mass makes space-time curved. And that explains how things move. You know, when you have gravity, it curves space-time and things move through space-time in the shortest possible, along the shortest possible path, which is a curved path, just like on the Earth. The Earth is round, and if you want to go to from point A to B, you don't draw a straight line. I mean, you're confined to the surface of the Earth, and it has to be a great circle. In other words, a circumference of the circle that passes through those 2 points. That's the shortest path. If you start reading about navigation by aircraft, they follow what are called great circle paths. Those are the shortest paths actually between 2 points on a globe. And it works the same way in four-dimensional space-time, actually. Although our minds, we only can think kind of in three-dimensional space, so we can't picture a fourth dimension. But anyway, it works though. The thing is, if it weren't for the correctness of general relativity, we couldn't make GPS work. I mean, we're all using GPS nowadays to go visit our relatives or find our way to a certain store or find our favorite fishing hole. But GPS is based on communication with satellites that are thousands and thousands of miles above the surface of the Earth. At that altitude, the gravitational field is weaker, and time passes just a little bit differently, a little bit faster for something in a weak gravitational field than something in a stronger gravitational field. That very tiny difference, you know, the clocks, if you could put a very precise clock on a satellite that's way orbiting above the Earth and compared it to a clock on the surface of the Earth, they would get out of sync over time. And that's due to general relativity. And they need to make those calculations to make corrections so they get the time to synchronize between those two clocks. And that's necessary for GPS to work because, you know, where those satellites are moving in space, we need to know where they are precisely. And to know where something is, you need to know what time it is also. So all this coordination of time and position requires general relativity calculations. So all these what were once considered crazy ideas make the world work, the human technological world anyway, work the way it does. Quantum mechanics, without quantum mechanics, we couldn't build these computers. We couldn't have MRIs, smartphones. The smartphone cameras are based on a quantum mechanical effect that Einstein actually explained also in 1905, called the photoelectric effect.
Wow, that's
These are
that's
all
very
products.
interesting.
What
That,
was
that
that? I'm
I
sorry.
just said that's very interesting. I didn't know that, especially about the MRIs too.
Yes, the MRI is actually, MRI was originally called NMR, for nuclear magnetic resonance.
Huh.
And it was developed to study the behavior of the nucleus of the atom. But people found out that that signal you get, I mean, it's the nucleus of the atom is like a tiny magnet, and they hit it with a strong pulse and make that magnet. It's like a gyroscope, you know, magnetic gyroscope, and the gyroscope precesses, and when it does that, it sends out a signal, a weak signal that can be detected, and you can use that signal to actually peer. You know, they were trying to understand the structure of the nucleus, but then there was an application found for that allowed us to called tomography, right, where you can reproduce an image based on those signals. So they're using so MRI stands for magnetic resonance imaging, which is a nicer term. People don't like the sound of nuclear magnetic resonance, but it's the same technique, but it's an application specific for reconstructing images based on how the nuclei of atoms in our bodies respond to, when they're in a strong magnetic field, how they respond to an electromagnetic pulse. But despite the name, it's not, you know, it doesn't deal with any harmful radiation. It deals with very strong magnetic fields, which apparently don't really affect people that much. But you know, it's safer than CT scans, which is basically a lot of X-rays going through you all the time. And you know, it provides amazing images of how we're, you know, of our insides. But yeah, that was a product of some physicists at I think Columbia University who were doing research on nuclear physics. The transistor is an application of quantum mechanics, and the transistor, some people consider the most important technological innovation of all time, because without transistors, we wouldn't have any of this modern electronics that we have today. Let's see. It's funny, I'm seeing chat bubbles coming up, but when I go into the chat area, I don't see the. Wait, let me. Why isn't it showing up? Okay. So, okay, Marissa said something here. So I had a thought about what you said about time and space. I thought about black holes and how they distort space and time. Yeah, so black holes are an extreme case where you know, gravity is so strong around, you know, mass has been compressed to such a high level that the gravitational field is so strong that light can't escape from it. That's why we call it black holes. But we can find examples of, like in the core of our galaxy, we see stars orbiting rapidly, a huge mass, but we don't see that mass. It's just an empty space that stars are orbiting. So there's a source of a very strong gravitational field in the core of our galaxy. It's called Sagittarius A, and it behaves, you know, when they calculate the mass and how much mass is in that space, it's consistent with it being a massive black hole. And there's a lot of other systems that are emitting X-rays, and could be explained as black holes accreting, you know, sucking in matter and heating it up as it gets compressed before falling into the black hole. and it gets so hot that it produces X-rays. So yeah, black holes, no one's ever traveled to a black hole yet, but we see examples out there that are consistent with there being black holes for real. Yep. So now whether or not then you start reading science fiction and you read about wormholes and jumping, jumping across the universe in a very short time, that's very speculative. I don't know if that's really physics or science fiction at this point, but there's some basis in that thinking that's not totally nuts. But black holes are pretty much accepted now. That's kind of standard physics. All right. I'm ready. It's 10 o'clock almost my time. So I'm ready to say goodnight to everyone. Thanks for joining. Thanks for asking questions. And, I don't always know the answer to things, but I'm always happy to talk about some stuff. So if you want next week, if you come with some questions, it can be off the wall and I'll take a stab at them. And some of you might know more about certain things than I do. So, I leave it up to you to answer sometimes. All right. Good night, everyone. I'm going to stop the show.
Good night, everybody.